In this lesson, we shall state Newton's first law of motion, describe applications of Newton's first law of motion, and describe the term inertia. Newton's first law of motion states as follows. Every body continues in its state of rest or of uniform motion in a straight line unless compelled by some external forces to act otherwise. Simply put, if an object is at rest, it will remain at rest until an external force is applied in order to move it. And if it is in motion, it will continue moving with constant speed in a straight line, that is, continue moving with constant velocity until an external force is applied to either slow it down, make it move faster, or change direction of motion. When an object which is at rest starts to move, its velocity changes. When the direction of travel or magnitude of the speed changes, there is a change in velocity. When the velocity of an object changes, the object is said to accelerate. In other words, a force is required to accelerate the object. This law is perfectly in line with what we have learned about effects of a force. We have previously stated that a force can affect the motion of a body in several ways. We did specifically state that a force can make an object which is stationary to start moving. It can also make an object which is moving to slow down, that is decelerate, speed up, that is accelerate, or change direction of motion. This topic gives us an opportunity to study effects of a force in depth. The first law of motion appears to be like an obvious fact. It's common sense that an object at rest does not just start to move on its own accord. A force must be applied on it to cause it to move. Put a book on the table and it will remain there indefinitely until someone picks it up. That is, until someone applies a force to move it. Similarly, an object in motion will keep moving in the same direction unless a force is applied to it to cause it to slow down and eventually stop or change direction. This second part of the law is not obvious to most of us. For instance, if you kick a ball, it will slow down and eventually stop. Why doesn't it keep moving indefinitely? There can be only one explanation. There must be external forces opposing its motion so that it slows down. One of these forces is air resistance. Resistance or friction is one of the forces which tends to oppose the motion of objects. Another force that exists with us is gravitational pull, or the weight of the object. A ball thrown upwards will rise with decreasing speed to a certain maximum height, where it is momentarily at rest and then accelerate downwards. Why does it slow down as it rises and speeds up as it falls? When it is rising, the gravitational force on it, that is its weight, is in the opposite direction. Its weight opposes its motion, so it tends to slow down. When it is falling, the force on it, that is again its weight, is in the direction of movement of the ball. This time, the force tends to accelerate the ball. These two forces tend to prevent the second part of the first law from taking place. Suppose we were to eliminate these two forces. Would objects in motion maintain constant velocity indefinitely? Absolutely. And this is what happens in deep space, where there is no air resistance or gravitational pull. When an object is very far from the Earth or any other massive object such as a planet, then the gravitational pull on it due to the planet is very small and therefore insignificant. In addition, there is no air resistance in deep space. It is a vacuum. If these two conditions are fulfilled, then Newton's first law would apply perfectly. Objects once in motion would continue to move at constant velocity indefinitely. No engine would be required to keep them moving. This means a spaceship would be able to save on fuel. The only point fuel would be required is to slow down, accelerate, or change the direction of the spaceship. So let's summarize some of the applications of the first law. Number 1. A person riding a bicycle on a level road does not come to rest immediately. He stops pedaling. The bicycle continues to move forward. That is, it continues in its state of motion. It eventually comes to rest as a result of the retarding action of air resistance. These forces make it to slow down and eventually stop. That is, change its state of motion. Application number 2. When the brakes of a car are suddenly applied or there is a head-on collision between two vehicles, passengers are jerked forward. More often, this leads to injury. Why are the passengers jerked forward? One may think that there is a force that tends to push them forward. There is no such force. The passengers have a tendency to keep moving in a straight line in the same direction that the car was moving. But the car has slowed down, so they slide off their seats in the forward direction. The passengers have a tendency to continue moving in the same direction. This is precisely why it is recommended that passengers should always put on safety belts. The safety belt prevents them from sliding off their seats forward in the event of a collision. The belts, however, should be elastic to reduce the impulsive force on the passengers. They should also be wide enough to prevent too much pressure being exerted on the passengers by the belt. We shall see this aspect in Newton's second law of motion. Let's look at a third application. This application involves movement of planets around the sun, or the movement of a celestial body such as the moon around the earth, or even the movement of a planet around the earth. Planets continuously change direction as they revolve around the sun. This is due to an external force on them by the sun. There exists a force of attraction between the planet and the sun. It is this force of attraction which is responsible for the circular path of the planets. For example, in this simulation, the Earth exerts a force on the moon in a direction which is perpendicular to the instantaneous direction of travel of the moon. This is the moon, and this is the Earth. This is the path of the moon around the Earth. It is a circular path. This blue arrow shows the force of attraction on the moon by the Earth. It is this force which makes the moon to travel in a circular path around the sun. This force is always perpendicular to the direction in which the moon is moving at that instant. The direction of travel of the moon at that instant is a tangent to the circle at that point. So you can see the force is always perpendicular. This force makes 90 degrees with the instantaneous direction of travel of the moon. Because of this fact that the force is always perpendicular to the direction of travel of the moon, the path of the moon around the earth is circular. Now, what would happen if this force were to cease to exist? Watch the simulation carefully as I switch off the force. Watch it carefully, and here I switch off the force. Do you see what has happened? We have lost the moon. The moon flies off at a tangent to the circle. If this force were to cease, then the planets would continue to move in a straight line, making a tangent with its original orbit. So you can see that this force is very important when it comes to motion of planets around the sun or any other celestial body. A spaceship in deep space can put off its engines and still continue to move at very high speed in a straight line. This is possible because there are no external forces acting on the ship in deep space. There is no air resistance and no gravitational pull. Now let's note the following points. Bodies on Earth slow down because of the existence of air resistance due to the air itself and with the surface on which the bodies are in contact. Gravitational force tends to slow down bodies which are moving against gravity. If the object is moving downwards, then the gravitational force tends to increase its speed downwards. That is, it tends to accelerate the object downwards. Once a body is moving with uniform speed in a straight line, it needs no force to keep it moving, provided no external forces are acting. If an external force is applied on it in the direction in which it is moving, then its speed in that direction will increase. That is, it will accelerate. If the force acting is in the opposite direction, it will slow down. That is, it will decelerate. If the force acting on it is in a direction which is perpendicular to its direction of motion, it will move in a circular path. Another point that we note here is that it is wrong to say that when a body is at rest, then there is no force acting. This will only be true in deep space. Take, for example, a book on the table. There are two forces acting on the book. Its weight, which acts vertically downwards, and the normal component of the contact force on the book, that is, the normal reaction. This force is exerted on the book by the table. These two forces are equal and opposite. This makes the resultant force on the book to be zero. So it continues to remain at rest because the forces acting on it balance out. It is important to realize that it is the resultant force which makes objects to change their state of rest or their state of motion in a straight line. It is not just the application of a force, but the resultant force. It would therefore seem reasonable to say that a body continues in its state of rest or uniform velocity unless a resultant force acts on it. It is clear that it is the resultant force which makes objects to change their velocity. We have already seen that if the velocity of an object changes, then the object is accelerating. We shall see this in the second law of motion. Now let us consider a new term that is important as far as Newton's first law is concerned. This term is called inertia. Inertia is the tendency of a body to remain at rest, or if moving, to continue its motion in a straight line. Bodies at rest or in motion have inertia. For this reason, Newton's first law of motion is often called the law of inertia. Bodies which have more mass have more inertia than those which are lighter. It is much easier to move a smaller object than a bigger one. The smaller object has less inertia than the bigger one. Mass is therefore a measure of how much inertia a body has. Similarly, it's more difficult to stop a moving lorry than a small van. The lorry has more inertia than the van. A better term to use here is momentum. Momentum is a derived physical quantity. We shall define momentum in the next subtopic when we talk about Newton's second law of motion. So let's stop this lesson by recapping the main points as follows. Point number 1. Newton's first law of motion states that every body continues in its state of rest or of uniform motion in a straight line unless compelled by some external forces to act otherwise. Point number 2. Inertia is the tendency of a body to remain at rest or if moving to continue its motion in a straight line. Thus, Newton's first law of motion can be referred to as the law of inertia. Thank you for listening, and I will see you in a moment where we will study Newton's second law of motion.